After studying this module, you shall be able to know about the various coordinated, tetracoordinated geometries. Also, you will learn how the crystal field splitting occurs in the presence of tetrahedral Ligand field. You can also identify the atomic orbitals involved in the tetrahedral bonding, and you will understand how the atomic orbitals combine together to form the molecular orbitals. Introduction to the tetrahedral complexes. Tetracoordinate in coordination chemistry refers to four ligands or atomic attachments to a single metal center. Tetracoordinated species can form tetrahedral, square planar or pyramidal geometries. In this module, we will study the molecular orbital theory for the tetrahedral complexes, which can be used to construct the molecular orbital diagrams for the complexes.
Now we will discuss about the tetrahedral geometry. First of all, we will discuss the geometry and the hybridization given to it. In a tetrahedral molecular geometry, a central atom is located at the center with the four substituents located at the corners of a tetrahedron. The bond angles are 109.5 when all the four substituents are the same. The perfectly symmetrical tetrahedron belongs to the point group TD, but most of the tetrahedral molecules are not of such high symmetry. One of the most common examples of tetrahedron geometry is a methane molecule having four equivalent covalent bonds between the central atom and the four hydrogens. The hybridization of 1s and 3p orbitals lead to the four sp3 hybrid orbitals for the bonding. This has been represented in figure where the hybridization of 1s and 3p orbitals to give sp3 hybrid orbitals in the methane CH3 molecule is shown. The next thing we will discuss is the tetrahedral ligand field. In the case of the coordination complexes, the tetrahedral geometry refers to the presence of central metal ion or atom with four surrounding ligands in a tetrahedral fashion via coordinate bonds between metal and the ligands. The effects produced on application of the ligand field to the free metal ion have been greatly concerned to octahedral fields because it is easy to visualize ligands and orbital orientation and points at the vertices of an octahedron that lie on the Cartesian axis. The effects of the ligand field are different for species with different geometries other than the octahedral one. In case we are talking about the tetrahedral field, the ligands are sited at opposite corners of the cube which circumscribes the octahedron. Therefore, orbitals directed in between the ligand for octahedral orientation are then directed toward the ligands in the tetrahedral orientation and the vice versa. In the case of the tetrahedral complexes, the situation is quite different from the octahedral complexes. Now, in this case, the approach of the ligands is in between the axes instead of along the axis, as was in the case of octahedral complexes. Consider a tetrahedral complex placed inside the cube with metal ion in the center and ligands occupying four alternate corners of the cube. Thus, rest four corners of the cube remain empty. In this particular situation, the orientation of the EG set of the orbitals is towards center of the face of the cube, and the three T2G orbitals point to the center of the edges of the cube. On the other hand, the angle between the T2G orbitals, metal and ligand, is 1/3 of the tetrahedral angle, that is 109 degrees 28 minutes should be divided by 3 to give us the value of 35 degrees 16 minutes. This is because the T2G orbitals are closer to the direction of approach of the ligands in comparison to the EG orbitals. Hence, this results in high energy of T2G orbitals rather than of EG orbitals, as was in the case of octahedral field. The process has been represented in figure. Also, the crystal field is much weaker for the tetrahedral complexes in comparison to the octahedral complexes, since the number of ligands has now been reduced to 4, as there was 6 for the octahedral case. The value of crystal field stabilization energy for the tetrahedral complexes is nearly 4/9 times that of the octahedral complexes. This is again depicted in the diagram shown. Next, we will discuss the molecular orbital theory for the tetrahedral complexes. First of all, we will discuss the sigma bonding in the tetrahedral complexes. To begin with, first of all, we need to set up a coordinate system in order to determine the sigma bonding orbitals in the case of a tetrahedral complex. It is shown in figure. The y-axis conveniently has been chosen to be the ligand axis. The d group orbitals has been represented as T2G and EG respectively. Figure the coordinate system for the tetrahedral ligand field. The symmetries of the molecular orbitals are to be determined by the identification of the atomic orbitals on central atom and the surrounding ligands. The atomic orbitals on the central metal, together with the corresponding symmetry adapted linear combinations, which is SALCS, named as SALCs, of the ligand atomic orbitals on the ligand atoms, will form the molecular orbitals that will be the basis for the representation that contribute to the reducible representation. In table 1, the character table for the tetrahedral point group has been shown. From the character table for the tetrahedral point group, it can be seen that the irreducible representation for the sigma bonding corresponds to A1 and T2. This means that the four atomic orbitals must be chosen so as to include an orbital of A1 symmetry and a set of three orbitals belonging to the T2 representation. The character table also tells us that atomic orbitals of the central metal atom falling into these categories. For the A1 group orbitals, we can have an s orbital. For the T2 group orbitals, we can have px, py, pz, dxy, dxz, and dyz orbitals. We therefore see that to form a complete set of tetrahedrali directed sigma bonds, the central metal atom will have to provide an s orbital as well as a set of p or d orbitals or both. We can now construct the molecular orbital diagram by combining the atomic orbitals of the central metal with the respective salks of corresponding symmetry on the ligands. In each of the cases, the combination can either be positive to give a bonding orbital, or it can be negative to give an anti-bonding orbital. The general form of the MO molecular orbital energy diagram for a tetrahedral metal coordination complex with sigma only type of bonding has been shown in the molecular orbital diagram. It shows the bonding between the metal orbitals with that of salks of ligands with proper symmetry. The Eg set of metal orbitals remain non-bonding since no ligand orbitals match with their symmetry. The tetrahedral geometry is electronically favored by D4 or D10 metal complexes where the non-bonding orbitals are either half or entirely filled. Next, we will discuss the pi bonding in the tetrahedral complexes. Pi bonding in coordination complexes is feasible with the availability of p or pi star orbitals in the ligands. Thus, here we will consider a class of ligands that are pi acceptors since they can accept electrons in their available orbitals, which is termed as pi back bonding. The concept is represented in figure. For such ligands, the normal bonding along with the back bonding also takes place. The bonding is synergic with respect to the back bonding, which means a sigma donation refers to bonding to the metal reinforces, or we can say increases, the pi back bonding to the ligand, and pi donation from the metal to the ligand fortifies the sigma donor component of the bonding. This happens because sigma donation leads to increased electron density on the metal, which allows amplified or increased pi back donation. Conversely, pi back donation reduces the amount of electron density on the metal, which allows more sigma donation from the ligand to the metal. The energy of a filled pi acceptor ligand is low in comparison to the metal T2G orbitals. The empty pi star orbitals are close enough in energy to the metal d orbitals to allow population. The examples of such type of ligands included CO, Cn negative, N2, etc. In these cases, we are talking about the pi bonding in tetrahedral metal complexes along with the sigma bonding. In this case, we have to understand that the pi orbitals are difficult to analyze in comparison to those of sigma ones. Once again, y-axis is chosen as the direction of the ligand axis with x and y axis perpendicular to the plane having z axis. From the character table, the irreducible representation for the pi bonding comes out to be E, T1 and T2. Now, T1 has no matching metal atom orbitals. E matches to that of dz square and dx square y square. T2 matches with that of dxy, dxz and dyz orbitals. The E and T2 interactions tend to lower the energy of the bonding orbitals and increase the energy of the corresponding anti-bonding orbitals. This results in the net increase in the value of delta T, which is the crystal field splitting parameter for the tetrahedral ligand field. Let us take an example of the tetrahedral complex showing sigma as well as pi bonding. We can have a nickel carbonyl complex where we can have nickel as the central metal ion and carbonyl CO as the surrounding ligand. CO is carbon monoxide, which is neutral ligand and has the capability to work as a sigma as well as a pi ligand. It is a sigma donor and a pi acceptor ligand. It has HOMO of sigma 2p symmetry and LUMO of pi star 2p symmetry. HOMO is said to be highest occupied molecular orbital, whereas LUMO is lowest unoccupied molecular orbital. CO is a ligand with good Lewis character as it is a good Lewis base and a sigma donor from the carbon atom. Also, the vacant pi star orbital LUMO can act as an electron pair acceptor capable of forming metal ligand pi bonds. The bonding pi orbital of the molecular orbital diagram is populated and is largely localized on the oxygen atom because oxygen is more electronegative in comparison to that of carbon. Hence, the lower energy pi bonding orbital is mostly oxygen in character. The antibonding pi star orbital of carbonyl has its largest amplitude on carbon and has appropriate symmetry and energy to overlap with that of T2G orbitals of the metal center. Because of the resulting energy correlation, the pi donor ability of CO is relatively small, and its bonding to metals is dominated by its pi acceptor character along with its sigma donor ability. The molecular orbital diagram for the nickel tetracarbonyl complex has been represented in figure 6, which shows a tetrahedral complex with sigma as well as the pi bonding. In the figure, it has been shown that the orbitals and their relative energies for the nickel tetracarbonyl complex, in which the interactions are that of CO, sigma and pi orbitals with the metal orbitals, are small. Much of the bonding is from metal to ligand pi bonding. There can be cases where the d orbitals are less occupied and the sigma bonding will be relatively important, which shifts in the positions of A1 and T2 orbitals to the lower levels and the 4s and 4p orbitals to the higher levels in terms of energy.
Summary. Tetracoordinate in coordination geometry refers to four ligands or atomic attachments to a single metal center. In a tetrahedral molecular geometry, a central atom is located at the center with the four substituents located at the corners of the tetrahedron. In case of coordination complexes, the tetrahedral geometry refers to the presence of central metal ion or the atom with four surrounding ligands in a tetrahedral fashion via coordinate bond between metal and the ligands. In the case of the tetrahedral complexes, the situation is quite different from the octahedral complexes, since now in this case the approach of the ligands is in between the axes instead of along the axis, as was in the case of the octahedral complexes. Considering a tetrahedral complex placed inside the cube with metal ion in the center and ligands occupying four alternate corners of the cube, thus rest four corners of the cube are empty. In this situation, the orientation of the 2 set of orbitals is towards the center of the face of the cube, and the three T2G orbitals point to the center of the edges of the cube. This is because the T2G orbitals are closer to the direction of the approach of the ligands than the EG orbitals, which results in high energy of the T2G orbitals in comparison to that of EG orbitals. For the tetrahedral point group, it can be seen that the irreducible representation for the sigma bonding corresponds to A1 and T1, and that for the pi bonding corresponds to E, T1 and T2. Molecular orbital diagram can be constructed by combining the atomic orbitals of the central metal with the respective SALCs of the corresponding symmetry of the ligands. In each of the cases, the combination can either be positive to give a bonding orbital or it can be negative to give an anti-bonding orbital.